Fusion Mobile, quality e-learning experience on the go.
My dearest, I hope you're still with me. Today we are looking at elastic properties of solid. May looking at the currents there, you will see how straight it looked, but yet it didn't cut off. And when you leave it, the inscription is that it will go back to its normal size and shape. So when a body can go back to its normal size and shape, we start talking about elasticity. A body is said to be elastic if it regains its original shape and size after undergoing stretch or compression. In a simpler language, it simply means that elasticity is the process by which a body can regain its size and shape after being distorted by force. There is a law that governs elasticity, and that is Hooke's law. Hooke's law states that provided the elastic limit is not exceeded, the extension E in an elastic material is proportional to the load or applied force. You can also rephrase it by saying Hooke's law states that the extension created in an elastic material is directly proportional to the force applied as long as the elastic limit is not exceeded. Mathematically, Hooke's law can be given as force is directly proportional to extension. And as we know that proportionality is a dummy sign, we have to bring in an equality sign, so we introduce a constant. So we'll say that force is equal to Ke, where K is a constant of proportionality known as stiffness or elastic constant. Young modulus. This is the ratio of shear stress to strain. Mathematically, it is given as Young modulus, sometimes represented as with E and sometimes represented with Y. But I would like us to work with E. That means E is equal to tensile stress divided by tensile strain. That means Young modulus is equal to X over X, or XT all over XR, where XT is giving us stress and XR represents strain. Now I would like us to discuss stress and strain. First of all, talking about stress. In definition, we can say that stress is the ratio of the force applied per unit area. Mathematically, stress ST is equal to force applied all over area. Bringing these to units, you know that force is represented in Newton and area is in meter square. So the unit of stress is equal to Newton per meter square. While talking about strain, we can also define strain as the ratio of the extension created to the original length. So mathematically, we can say that strain SR is equal to extension all over length. In units, we know that extension is represented in meters and length is also represented in meters. So meter will go to be meter and we have 1. And when the unit of a particular parameter is 1, we'll say that the unit is unity, and that means that it is dimensionless. So from here, we can discuss work done in an elastic material. In work done in an elastic material, mathematically is given as the average force, F average, times the extension created. As we know, that force average times extension, formally we say that work done is force times displacement. But this time, work done is also force, but the force here now is talking about average. That means we will be talking about the first force plus the second force divided by 2. For example, in an elastic material, before we load the spiral spring, for example, before we load the spiral spring, there exists a certain force. Example, gravitational force. We can consider it F1. And when we load, we now have another force, which may be as a result of the load. We can consider that F2. So F average here will be F1 plus F2 all over 2. But don't forget that F1 plus F2 is the total force, F. So, if F1 plus F2 is the total force, we can now say that work done in an elastic material is equal to F, which is the total force, which is F1 plus F2, divided by 2 times extension. So we'll say that work done or energy stored in an elastic material is half Fe. And knowing what F is from Hooke's law, F equal to Ke. So we can continue from here and say that since work done is equal to half Fe, that means work done is equal to half F. Now replacing it with Ke, we'll have half times Ke, then times E, which means that work will be equal to half times K, then E times E. What do we have? We'll have what? E square. And work done in an elastic material is half K E square. Please don't mix it up with Young modulus of stress and strain. Taking it back to work done here, we'll say that work done is equal to half Fe. And you can note all this in materials like spiral spring and many other elastic materials, even the rubber band you play at home. After this, we'll go into something else, which we call crystals. What a lovely crystal there. Is it not looking beautiful? So meet me in that class. It will be very enjoyable.